Okay. So these are, what we're working on here are called multi-stage probabilities. Multi-stage probabilities. So we talked about single stage, and we jumped into two-stage probabilities a little bit with the spinners, one person playing against another for fair games. And on the first day of probabilities, we talked about flipping 2 coins, heads and tails, which is another multi-stage probability. So I'm just going to do a few problems related to this. I'm going to keep it just with 3 stages for now, but you can easily extend this to 4 or 5. Once you get beyond 5, the pictures get harder to draw and other techniques are needed. The book has another section that presents other techniques, but we don't have time to cover it. So we're just going to stop at like 3 or 4 stages. So I am from a family of 3 kids. And I am the oldest, so the boy, and then my brother was born next, and then the girl, my sister, was born third. And there are lots of families that have 2 boys and a girl. And so what I want to look at are what are the possible family configurations for 3 kids? What does it look like? And we could just kind of start writing down ideas like, oh yeah, it could be boy, boy, girl, it could be boy, girl, boy, and so on, but we want to be careful not to miss anything. And a tree can help us collect all the options. And there's different ways to make the tree. These kind of evolve in time, right? Firstborn, secondborn, thirdborn, and so that is kind of an obvious way that the tree could be designed to deal with that. So that's the way I'm going to draw mine. So the first part of my tree branches off twice because there's only 2 options. Our spinner, remember, had 3 options. And either the first child is going to be a boy or the first child is going to be a girl. And then each of these is going to need to branch. I'm going to switch colors for this branch. So for the second child, if they had a boy, they could follow that with another boy or a girl. And similarly down here, this first girl could be followed by a boy or another girl. So this is kind of like the heads, tails thing with flipping 2 coins. It's the same tree. We just replace boy and girl with heads and tails. We have a third child, though, so every one of these endpoints has to branch again for a boy or a girl. So branch each of these out, boy, girl, boy, girl, boy, girl, boy, girl. And there's multiple things to consider here, what's going on. One thing I know if I look at the tree, when I look at the ends, there's 1, 2, 3, 4, 5, 6, 7, 8 different outcomes. So I talked about in the beginning of this class, and the book talks about this, the idea of a sample space. A sample space, or what are all the possibilities? So this tree has 8 different possibilities for us. Other ideas that came up before was the idea of equally likely. Are each of these 8 equally likely? Are probabilities always equally likely? So first, are probabilities always equally likely? Any things that can happen? Or sometimes is one thing more likely than another? Think about the free throw idea we talked about the other day. Equally likely outcomes, in or out? No. Yeah, so most things aren't equally likely. Some things are. Do we believe you're just as likely to have a boy as a girl? That's kind of believed. It turns out if you look at the statistics, women are slightly more likely to have boys than girls. But strangely, there's more women on the planet than men. Why is that? Because boys are more likely to take themselves out of the gene pool sometime in their youth. They're more likely to die at a young age. They're more likely to take a risk as children, adolescents, and young adults, and they die off. Right? Maybe it's testosterone. Maybe there's something else going on. I don't know the biology of it, but it is an interesting thing that happens over time. There's more male births slightly than females, slightly more than half, yet overall there's more women than men. So what are the possible outcomes? To get a possible outcomes, I have to follow a branch. So following that top branch all the way up there, one option is that there could be a boy, and then a boy, and then a boy in that order. To get another branch, I'm going to have to go boy, boy, and then grab the girl here. So we just, off each endpoints, we look back to see where it originated. So then we're going to have boy, boy, girl as an outcome. Then boy, girl, boy is the next one. And then boy, girl, girl. We've exhausted all of these starting with the first boy, so now we get a first girl to start with. Girl, boy, boy. Girl, boy, girl. Girl, girl, boy. And girl, girl, girl. Other thing to consider is, does order matter? So, for example, I have boy, boy, girl, that second one, which is the way my family turned out. Is that different than boy, girl, boy? They both have 2 boys and 1 girl. Does order matter? And the answer is it depends on the question.
Not if we're going by like chronological.
So if the question was like, how many boys are there in a family of 3? Order doesn't matter. If the question was, there's a firstborn, there's a secondborn, there's a thirdborn, then it does matter. And here, I think in most families it matters. There's some significance between firstborn or secondborn or thirdborn. So it does matter. As far as counting goes, there's a couple ways to look at that, and we'll count that up in a minute. How many outcomes are there again in this situation of 3 children?
8.
There's 8 outcomes. So what does the sample space look like? The sample space are these things I wrote down over here, these 8 different combinations of G, G's, and B's. Okay. Is just a boy part of the sample space? The answer is no. Boy, boy, boy is part of the sample space. Boy, boy, girl is part of the sample space. So the sample space is one end product that we're looking for. And we are just looking at families of 3 children. So the sample space would be those 8 different configurations of boys and girls. So what's the probability a family has a boy, then a boy, then a girl?
That's where I kept getting confused because, do you increase your 50%? Because, doesn't it say 50% chance every time?
So there's 2 ways to look at this to come up with an answer for that. So one way to kind of figure out what happens next is to explore the idea of equally likely probabilities. Something's wrong with that. Let's go with it. Equally likely. So boy versus girl birth is about equally likely. We usually say you're just about as likely to have a boy than a girl. Statistics show boy is slightly more likely, but it's barely. It's close enough to 50% if you round to like the nearest 10th. So when events are equally likely in our tree, there's no need to label the probabilities on each branch because they're the same everywhere. So we don't bother. Okay? So if these 2 events are equally likely, that means these 4 events are all equally likely, and these 8 events are all equally likely. So all my endpoints are equally likely. There's 8 possible outcomes. They all have the same probability, 1/8 each. So the probability of getting a boy, then a girl, 1/8. Okay? So based on the initial assumption, and again, this is an assumption right here, based on that assumption, then the probability of a family having a boy, then a girl is 1 out of 8. That's 1 of 8 possible outcomes for a family of 3. Summarize a package for you. Sample exit exam, back page is optional, required take-home exam.
Can we just only do take-home part time?
We'll do a little in-class part too. Actually, the in-class part will be about the same size. It's about 50-50 on the test. So sometimes the outcomes aren't equally likely, in which case we should label the tree like we did label some trees last time. So I'm just going to go back and do that here. The probability of getting a boy is 0.5, 1/2, right? And the probability of getting a girl is 1/2, 0.5. And that continues up the tree. After you have a boy, you're just as likely to have a boy again or a girl. And so every one of these branches has a weight of 0.5. So I could put them in there. If they weren't all equally likely, we have to write them in there. Otherwise, we can't answer any questions. All right, I think I got them all. So to calculate the probability when the weights are in the tree, you multiply when you move through the tree. So 0.5 times 0.5 times 0.5. So what's 1/2 times 1/2 times 1/2? 1/2 times 1/2 is what?
20.
A quarter, or 0.25. Let's stick with fractions for a minute because we got to review them. 1/2 times 1/2 times 1/2 is, what is it?
Wait, 1/8.
1/8. Yes, which is what we thought when we just said, hey, they're equally likely. Yeah. So it turns out if they're equally likely, you get the same answer if you just assume since the beginning was equally likely, the end will be equally likely. Or if you actually write those probabilities and multiply them through. Making a little sense? We'll do more examples of this in a minute. All right, so let's go ask another question. What's the probability, what color? What's the probability of having a boy, then a girl, then a boy? Okay, 1/8. Okay. What is the probability of having a girl, and then a boy, and then a boy? 1/8. Okay. A little harder. What is the probability of having 2 boys out of 3 children? Three-eighths. So in this system right here, because I'm looking at what happens with 3 children, this is one of 8 possible events, right? This is one simple event in the sample space. This is not simple because there's more than one way that can happen. So I'm just going to break that down on another page. The probability of having 2 boys out of 3 children is the probability of having, say, it could be boy, boy, girl, or it could have been boy, girl, boy, or it could have been girl, boy, boy. Those are the possibilities. Sometimes those ors can be rewritten as a plus. So probability of boy, boy, girl, plus the probability of boy, girl, boy, plus the probability of girl, boy, boy. In which case we have 1/8, and 1/8, and 1/8, which equals that 3/8. In the reading, does anybody recognize the phrase mutually exclusive? In the reading. Can anybody think and remember what mutually exclusive means from the reading?
Words like just specific to something?
Just specific to some things.
Like, was it part of one of the equations that was shown or no?
It was part of an equation and it was part of a couple of problems, yeah.
Was it the
Let's break it down. What is-
so on
Okay.
one of the equations I was doing, it was
Yeah.
like your probability, and for example, it was R. So then you times it by that minus 1 to where.
That's the idea of independence. We'll get to that next.
Okay.
Yeah. Okay, so that's similar but different. Yeah, so what does exclusive mean? Well, it means exclude, right? Mutual means together. So together they exclude. Mutually exclusive means they have nothing in common. Okay? So is a boy then a boy then a girl the same configuration as a boy then a girl then a boy? Or are they different results in our tree? Aren't they each a different line in the tree? Yeah. So they are what we call mutually exclusive events. They don't have anything in common. If they don't have anything in common, then we're okay just adding them straight together. We don't have to worry about any overlap they might have. And they just work out fine. Alander was talking about a different idea called independence. So again, each of these are mutually exclusive, so they add nice. The idea of independence, Alondra mentioned from her notes in a problem she was working on. So it's a slightly different idea. Independence means one event doesn't affect another. So, for example, the probability of the second child being a boy when the first child was a boy. Okay, so my mother had me. What's the probability her next child is going to be a boy? What is it? The next child. So she's going to have a baby. Is it going to be a boy or a girl? What's the chance it's going to be a boy? 50%. Right? So it doesn't matter that the first child was a boy. It's still 1/2. Okay? So without this extra information doesn't change anything. That's what independence means. It's still 50%. It doesn't change. Okay? Places where events aren't independent. If somebody shoots a free throw and they get it in the first time, might they be more likely to get it in the second time? That they feel confident and they might get it in, they miss, they're nervous on the second shot, maybe they won't. That's been studied. There's a little evidence that if they get it in the first time, they're more likely to get it in the second time. So maybe on their first shot, they have like a 60% free throw average, but their second shot might be 70%. A little higher if they got the first one in. So sometimes things are independent, sometimes they don't. We always have to question that. So that kind of goes back to my tree here. The probabilities didn't change from one stage to another, and a stage is when we make a new set of branches. Oh my gosh, what did I do? Let's try this. When I move from the first child to the second child, the probabilities stay the same. That means they're independent events. We'll do an example next when they're not independent. Okay, so I want you to help me fill out this table for this set of probabilities. So one column, we're going to have number of girls. Good. And then in the next column, we're going to have probability. So for example, so we're still doing the family of three children. So what I'd like you to try and do is, what's the probability that there's no girls? What's the probability there's one girl, two girls, or three girls? So we want to fill out this table based on what we know, based on the tree we built. If you didn't copy the tree, try to redraw it right now real fast. We've already answered one of these questions. If a family of three has two boys, how many girls do they have? One. So we answered that question earlier. Try to answer the other three. So what do you think about no girls? Probability? That's one. Probability of one girl is three.
Oh.
Because we did that one earlier, because having one girl is the same as having two boys out of three kids. Remember, those out of three children. No girls, what's the probability? 1/8. If you have no girls, that means it must be boy, boy, boy. And that only happened once. Right there. Okay, what about exactly two girls, which means there would be one boy? What's that one? 3/8 is that one? Yeah, since there's really no difference between having a boy and a girl because it's 50%, having two boys or having two girls out of three is the same thing. What about three girls? Girl, girl, girl only came up once, so that would be 1/8. So with a family of three, are there any other possibilities for girls? 0, 1, 2, or 3? Aren't those the only possible ways you can have girls in a family of three? You either have no girls, one girl, two girls, or three girls. Okay? The other kids are boys, right? So these are all the possible ways of configuring girls. What do these probabilities add up to? 1/8 plus 3/8 plus 3/8 plus 1/8?
One whole.
One whole, or 100%. Yeah. Whenever you have all possible events organized in a way that doesn't have any overlap, it's always going to add up to 100%. Now, these aren't simple events, right? Having one girl, there's three different ways that could happen. So that was boy, boy, girl, boy, girl, boy, or girl, boy, boy. Those were the three different ways it could happen. That's where the 3/8 came from when we look back at the tree. But altogether, it adds up to 100%. Looking back at the original tree, when we run through the tree and take 50% times 50% times 50%, that we call that 1/8. As a decimal, it would be 0.125. What's the probability that we get a boy, boy, girl? 0.125. What's the probability we get boy, girl, girl? 0. They're all 12.5%. 0.125. What happens when we add up all of those 0.125s? It'll be 100%. Yeah. So this is important too. If you have all possible probabilities and they don't overlap, then it always has to add up to 100%. No more, no less. If it adds up to more or less, that means you have some rounding error, you missed something, you double counted something. One of those three things can happen. All right, ready to look at a more complicated question? Absolutely, let's do it. Okay, so we're still going to stick with a three-stage system, but we're going to look at playing cards. And some of the homework problems, I had it show a picture of a deck of cards all laid out, just in case, because I've had students that are like, I don't know how many cards are in a deck. I don't know what colors and suits, they just didn't know, right? And that's okay. Not everybody is expected to be familiar with that. But in this room, are we all comfortable with what a deck of 52 playing cards looks like? No. Okay. Let's just take a look at one so we can try and answer some of these questions.
Only from the homework.
Oh, because it showed up in the homework and you saw the picture? Yeah. Every year I get at least one, and that's okay. I mean, you'd be amazed at the stuff I don't know. It's shocking. Is it anyone? Never mind, that was a stupid idea. No, don't gamble. Gambling is dangerous and addictive. Well, I was trying to think of like amazing things other people didn't know. And the idea that came to my head wasn't a real situation. I realized as I thought it was from a movie, and so I didn't want to make a movie quote in class because that sounds stupid. Okay. Playing cards. Images. Okay, there we go. Come on. Come on, load the image, please. Doesn't want to load it. Can I get it here? No. Okay.
For the longest time, I didn't realize that spades weren't cards. I don't know.
That there was a difference?
Yeah, there's a difference. I was like, wow.
Okay, let's try one of these pictures. Does that show all of them? Yes. Okay, hopefully this one loads in a new tab. Oh, that's a little big. Okay, that's all of them right there. So, come on, get it. All right, anyway. So the regular set of playing cards has ace, which is like a one object on it. The 2 has 2, 3 has 3, 4 has 4, and so on. So I use these a lot with games with kids, like addition games, multiplication, subtraction, because you can actually, look and count and see the digit. When kids are learning their numerals, like preschool, this is a great thing to play with. Then you have Jack, Queen, King. So we have 1 through 10 plus the 3 suits, and then there's 2 colors, red and black, and there's 4 suits, spades, hearts, diamonds, and clubs. So that's what we have to work with in standard deck of cards. And what we're going to look at is the probability of getting 3 of the same kind when you dealt 3 cards. And we're going to try and map this out using a tree. All right, so we want to find the probability of 3 of a kind out of 3 cards. And the interesting thing, I have a first draw, right? There's going to be a second draw, and there's going to be a third draw from the deck. And I'm just hoping for 3 of a kind. I don't care which they are. I just want 3 of a kind. That's all I'm looking at calculating here. So in the first draw, any card will do. There are 52 cards to choose from out of 52 cards in the deck. So the probability for card number 1 is 100%. I got a card. Okay. Now, the second card, I'm hoping for 3 of a kind, right? It's either a match or it's not a match, right? Either I got the card I wanted or I didn't. All right, so let's see. Let's look at our picture for a second. Let's just suppose that I got the ace of spades, that card up in the upper left corner. That was my card. Okay. So, and then my second draw, I got a match. How many cards match that? There's 3 cards that match it. Okay. Do I have a full deck, by the way, on the second draw?
No.
No. Okay, so we got to take that into account too. So on the second draw, if it matched, there's 3 cards that match the whatever one I got. I'm just saying, hey, let's make believe it's the ace of spades. So it's one of those other aces. How many cards were in the deck for the second draw? 51. Right, because they give me the card, I got it.
Yeah.
Yeah. So so that's another thing. When you're drawing like marbles or cards or whatever, do the things go back in? Do you just look at it and put it back in the deck?
No, you keep it.
It depends on the situation, though. Sometimes it goes back in, sometimes it doesn't. Okay, like most lotteries, when a number pops out, it stays out. Some you pop it out, you look at it, you put it back in, and it could appear again. Okay, it just kind of depends on the rules of the game. So you have to always think: is do you replace the object or not? So this is without replacing it. As far as not, how many cards? Now I don't really need that number, but I want to put it in for fun anyway. How many cards don't match my ace? 52 minus those 4 would be 48. 48 don't match. So I don't really need it for this, but I'm going to put it in there for fun. There were 48 cards that didn't match out of 51. 48 plus 3, by the way, is what? The numerators? 51. It's all possibilities. Okay, so I'm trying to get 3 of a kind, so I don't really too care about that not over there. So either, when I draw again, either I get another match or not. This knot's a little bit, is it more complicated now? Not really. Okay, so let's see. How many cards are there left to match? I got an ace, I got another ace. Third card matches. How many aces?
2.
There were 2 possible aces to match. Yeah. Out of how many in the deck? 51. Or 50, yeah. Now, I want the probability of 3 of a kind. Is my tree going to lead to other ways to get 3 of a kind?
Not if you're only drawing 3 times.
I'm only drawing 3. This is 3 of a kind out of 3. I'm only drawing 3 times.
Oh.
So if I'm only drawing 3 times, is there any other branch that's going to lead to 3 of a kind?
No.
No. So I don't have to complete those other branches, but I could. Maybe we will in a minute. So let's see. Can we figure out the probability now? The answer is yeah. It's the product of the probabilities along the way, which are the fractions I was building here, here, and here. And so if I just write that out, I guess I'm going to stick it down here. I've got 52 over 52, which is going to reduce quite nicely in a minute, times 3 over 51, times 2 over 50. Now, I could just multiply straight across the top, multiply straight across the bottom. That would tell me the total possible 3-card hands, which would be interesting, and how many different ways you can get 3 of a kind out of the deck. So I usually do it both ways. So calculators, get them out if you don't already have them. Help me with these calculations. We need to know what's the product of the numerators here, what's the product of the denominators. Let's see, so we've got, I think the first one was 52 times 3 times 2. That gives me 312. And then what was it? 52 times 51 times 50. 132,600?
Wait, those 52 cancel out?
Yeah, I'm going to do it 2 different ways, I said. I'm going to calculate the straight numbers. I'll explain why I'm doing it 2 different ways. So what was the top? 312?
Mhm.
Out of 1,000, 100,000? Oh, shit, no, I forgot.
132,600.
Sorry, what was that again?
132,600.
600? Okay. So this tells me a couple of things. Out of all possible 3-card hands we could deal from the deck, there's 132,600 possible groups of 3. And they're all different. And then there are 312 ways to get 3 of a kind. 3 aces, or 3 twos, or 3 threes, and so on, up through all the different possibilities. 312 different ways that can happen. Because there are 52 different cards to choose from, any one of those 52 matches with 3 other cards, and then from those 2 cards, there's 2 others you can match with, and that gives all the possibilities. So that's one answer. That fraction is an answer, but the reduced one's always kind of nice too. So if we do the reduced one, 52 over 52 is 1. 2 goes into 50, 25 times. And it turns out 3 goes into 51 because 5 plus 1 is 6. I think it's 17 times. Can someone confirm that for me? Jamie's nodding. I think it's 17. Okay, so what's 17 times 25? Because that's what's in the bottom right now, 17 times 25. 425. And just for fun, what is 1 out of 425? What's 1 divided by 425? To like 4 decimal places.
0.0023.
Okay. So there's a 0.2% chance. 0.2%. If you want to put the 3 in there, we can put that in there too. Almost 0.25% chance. 23 out of 1,000. 1 out of 425. Not great probability, if that was the hand you needed. Doesn't happen too often. 1 out of every 425 tries. We get this to happen. All right, so we could either do one slightly harder version of this, or we could do some homework problems. The slightly harder version, by the way, I was going to say, what's the probability of getting 2 of a kind out of 3? And you might think, wow, it's only 2 out of a kind. That should be easier. It's slightly harder. Because think about the boy, girl, boy. Where's that different card? Is it the first card different, or the second card different, or is the third card different? Right, that makes our job count a little harder.
But you'd keep out of 3 the same. Yes?
Well, what just so instead of here I asked what's the probability of 3 of the kind out of 3? The slightly harder version of this problem would be to say what's the probability of getting only 2 of a kind out of 3. So you draw 3 cards, but only 2 of them match. The third card's different. It's slightly harder. We have half of the tree there to do it. We're actually halfway done with that problem. So, okay, nobody's that excited about this problem. Bummer. You don't play cards, none of you?
I mean,
Okay,
if it makes me feel better.
that's fine. There's some very interesting homework problems. Did anybody get stuck on a homework problem for 8-2?
Yes.
Oh, good.
I think there was 2 of them.
2 of them? Multi-stage. Okay, which number? Alon, do you remember which one was troublesome or
The
summer?
last one, like
The
I was
last
able
one.
to do the bottom part based on like the equation that I watched from the videos.
Yep.
But the top part was what you were kind of going over. But even then, I don't know why.
Okay, let's take a look.
The last one was 1 for Lindsay.
So same problem, slightly different numbers each time. Let's do it. Page, paste. All right, and then the questions. What's the probability that a male is selected, then 2 females? So a math class consists of 29 students, 16 are female and 13 are male. 3 students are selected at random, 1 at a time, to participate in a probability experiment. Ooh, lucky students. And we want to know, first, what is the probability Now, if we have a lot of questions to answer, it's not a bad idea to make a tree, because then once we have the tree, we can solve any question somebody asks. Or we can just apply a different strategy to each problem, right? So there's pros and cons there. So this one, I'll do it without a tree. One thing about this problem right here is, what is the probability as a male is selected, then 2 females? So we know the order. Male is first, then a female, and then another female. So we want the probability in that particular order. And these are one after the other. They're selected in order, right, without replacement. So once a student is picked, they can't get picked again, right? They're out of the thing to be chosen. So what that means is that these are not independent. So for example, the probability of getting that first male student is what? That one's the easiest one. How many males are there?
13.
13 out of a total of?
42.
Nope. 29.
Oh, sorry, I'm
Yeah,
looking
'cause-
at mine, sorry.
Yeah, okay, you have a different number there? Okay. Yeah, so it's out of 29. Yeah, so whatever your numbers are, it's the same process. That's the probability of getting this male, right there. Now, I mentioned they're not independent because there's not 29 students anymore, there's only 28 students left. The not independent changes the denominator. If they were independent, the denominator would stay the same. Like with a boy, it's 1 out of 2 the first time, it was 1 out of 2 for the second time, right? That's independence. Probability stays the same. These are not. How many females? So one male is gone. How many females are there still? 16. So that's that female right there. And again, think about, we could build a tree for this. You multiply as you move through a tree. I'm multiplying as I do this. Now, there's less students now. There's only 27 students left in the class to pick from. How many females are left? 15. And I think these problems usually wanted a decimal answer. Most of the time they didn't want a fraction. And so you could just multiply it into your calculator, get an answer, plug it in. So I'm going to get a decimal version of that one. Let's make sure we can all match the answer on our calculators. So whip out your calculator. This matters. Type that in any way you know how. That's the right one way to type it. I get about 14%. Everybody else get that? 14.2 to the nearest tenth for these numbers? No? Yes? Okay, I'm going to do it another way just to make sure.
Yeah, I got one.
You should not. So these are all fractions, proper fractions. The answer should be a proper fraction. So how many of you, when you were doing this, looked at it and said, okay, I got to take 13
Wait, we're
times
adding
16 times, we're multiplying. We're multiplying. Did you do 13 times 16 times 15 first?
I did not.
And then 29 times 28, 27? If you do it that way, you got to be careful because the 29, 28, and 27 have to end up in the denominator. And I got them in the denominator by, where'd you go? Saying it was 13 over 29 times 16 over 28 times 15 over 27. So another way to type that would be to say I've got, let's see, what do we start with? 13 males times 16 females times 15 females. But when I divide, I got to have parentheses for the denominator. 29 times 28 times 27, close parentheses, and I get the same 14%. Yeah, so it's about 14.2%. Usually when you click on the box, it says type whatever you want. So I could type all the fractions if I wanted to. 16 over 29, is that what I started with?
Yeah,
Times 16 over
28.
28, and 15 over 27, right? So I could type it that way, and it should say, sure. Or I should be able to type 0.1, what was it, 1423?
098.
Okay, so 4 decimal places is probably enough. Yeah, it said 4 decimal places is fine. So, but do be careful if it says some fine print about how to type it. Sometimes that matters. All right, so that one wasn't too bad. What is the probability that a female is selected first, then 2 males? That's a lot like this one. That's not bad. What is the probability that 2 males are selected, 2 females, then 1 male? What is the probability that 3 males are selected? What is the probability that 3 females are selected? So all of these can be done without a tree, just by thinking about what's happening each time and what's in the numerator and what's in the denominator. If we had more complicated questions to answer, a tree would be worth building. So a tree for this would look like the following. First try, male or female. What's going to happen second try? Male or female? Male, female. Third try. Same, male or female, male or female, male or female, male or female. Now, am I just as likely to get a male as a female? No. No, I'm not. So I have to fill in probabilities at each branch. So the first one was 16 out of 28 for a male. No, 29, I lied. And no, I got that backwards, didn't I? Males were 13, weren't they?
Yeah.
For my problem, 29, and this was 16 out of 29. So then we move over to you picked a male first, what happens next? There are less males, so there's 12, there's also less students, so there's 28. In this branch over here, have we lost a female yet? Not yet, so there's still 16 females, but there's only 28 students there. And so we can get the probability for each branch. The last one, how many males are left at the top?
11.
11 out of how many?
27.
27. Now I went male, male. No females have been selected yet. How many females are at the top? 16 out of 27. And so you just have to think about what's left at each stage. Okay? If I move on to the second row of red stuff, this went male, female, so I lost a male and a female. So 13 males, that means there's 12 left here out of 27. And I lost one of the 16, so there's 15 out of 27 there. So we can reason through the whole tree. A female is gone way down at the bottom here. How many males are left? Still 13 out of, wrong color, out of 29. And then females, I lost one, so I have 15. Oops, I lied. I have 28. This went female, male, so I'm down a male. So that would be from 13 to 12 out of 28. I lost a female, so how many females are there?
15.
15 out of, oops, I lied again. It's not 28, what is it?
29.
Not 29.
27.
27, yeah. Let's see, that's not an 8. Red, 7 out of 27. What about the final branch? We lost 2 females. How many males are there? 13 out of 27. There's still 27 in the third draw. How many females? A female is drawn, then a female is drawn. How many are left? 14. Yeah, so now that I have the whole tree filled out, I can answer any question by just tracing through the tree to find out what question needs to be answered. And I can get the probabilities. So one of my questions was, let's look at the last one. What is the probability that 3 females are selected? So all I have to do is look at the tree. 3 females would be the last one. And so I would just need to multiply the 3 numbers in that to get the answer for 3 females. Carefully on the calculator. This problem accepts fractions, so you can type them in as fractions. Not too bad? All right, was there another one that was troublesome?
I was able to do everything.
You did everything
Yeah.
fine? Okay. Yeah, 3 children, boys and girls. We just did that problem on the board, so the answer to question number 7 is in your notes. Marbles. This is much like the problem we just did, but we're just doing 2 marbles.
I think the videos help. That's
Yeah,
why
I
was
tried to
able
pick some of the problems with videos.
That's why, like, the last problem, I could answer the bottom.
There was one problem where I
Question.
didn't like the video, but I liked the problem. I put it in anyway, so my apologies. Can't remember which one it was, but let's try this one together. See if we can agree on an answer. Page. All right, so suppose a jar has 5 red marbles, 19 blue marbles. If you reach into the jar and pull out 2, bless you, 2 marbles at the same time, find the probability both are red. Give that a shot, see what you come up with. There's many ways to attack it. There's one correct answer, and there's still Mary and Dirty Pie up here.
In total,
And with cream.
so that makes for total 4. So, if you reach
One of the red marbles has a probability of 5 out of 24.
But you need to, you're
What's the probability for the next red marble? 4 out of... Uh-huh. That's the only branch that has both red. So I don't have to fill out the other branches, but I could. That simplifies a little bit. Does this want a fraction, decimal, or either? It says enter anything you want. So I could type 5 out of 24 times 4 out of 23. Or I could type a decimal.
Oh, it is
And I liked it. And again, be careful typing it in your calculator. Depends on your calculator how it types stuff out. On mine, I can type 5 out of 24 times 4 out of 23. And so probably 4 decimal places is enough. 0.362. Should be acceptable also. Yeah, it likes that too. Questions on that one?
Can we, sorry,
Another question?
can we do the Is it the deck of cards, or which one that we are finding like harder?
Do a harder probability problem? Yeah. And then that's a good ending because that's about as hard as the Pratt question I would ever ask. Let's see, I started a page for that. I think back here. Oh, there it goes. All right. So we need to draw a tree to figure out what's going to happen. We'll need to consider more of the branches because there's just more ways this can happen. So let's give it a try. See what happens. Just like before, any card I get at first in this situation is a good card. So for that first draw, so we're going to have to map what happens first, what happens second, and what happens third. Now, a deceiving thing, by the way, about that marble problem, they said you pull 2 marbles out at the same time. That's not like I pull out 1 marble and then the second, but it kind of is, because they're not the same marble. They're 2 different marbles. So you still have to treat them as stages, it turns out. And that's always a hard thing to wrap one's mind around. In this case, however, since I'm looking for 2 of a kind, and it doesn't matter whether I get an ace or a red card or a diamond, any card is fine. So there are 52 cards that are, I don't care which one I get, I'm happy, out of 52. From there, either the next card matches it, or it is not that card. Not like that first card. How many cards match the first card? And again, I usually, to think about something like this, I pick a card from the deck and say, oh, that's my first card. So let's just bring up that deck of cards again just to see it. Right? So maybe I got the king of clubs down here, bottom right. Okay? There's 3 other cards that match it. I have the king of clubs in my hand. That means there's 51 other cards out there. As far as cards that don't match it, there's 4 kings altogether. 52 minus 4 is 48. There's 48 other cards out there out of 51. Now, I want only 2 of a kind. So if I happen to have a match on my second card, for my next card, do I want it to match or not? I do not want it to match. Not. No, don't want it to match. Don't want it to match. Okay. So, so if it doesn't match, that means it's not a king. Because I was thinking my first card was a king. How many cards are not kings? 48 of them. Yeah. Now I have 2 kings in my hand. How many cards are left in the deck? How many? 50. Yeah, 48 out of 50. So that is one way to get exactly 2 of a kind out of 3. I got a king, and who cares what else? Okay. So, but could the draw have happened different? Is it possible I got a king, something else, and then a king?
Yeah.
That would be okay. All right. So we got to explore this other branch down here. Okay. So what can happen in this branch down here? Well, either I match the first card, which I'm happy about, right? Or let's see what else could happen. I don't match the first card, but could I match the second card?
Yeah.
I could. Now, there is a third option here that I don't match either. No match at all. But what happens there is I got the king, I got something else like an ace, and then I got something that wasn't a king or an ace. Does that meet my criteria up at the top? No. So I don't really care about that one down here. It's not part of what I need to count for my numerator. All right, so let's see. There I have a match for my king. I have 1 king in my hand. I have something else. How many kings are left?
3.
If I'm in this branch right here, I have 1 king in my hand. I have something else. There are 3 kings at that point. Out of how many cards? 50? Okay. I have some other card besides a king in my hand. Maybe it's an ace. How many other aces are there? 3 out of 50. And again, I don't care what happened down there. All right, so here's what I have going on. I have match, match, not. That's the top row. The second row is match, not, match. And the third row is not, but then match, match. The last two matched. Are those the only ways to get 2 of a kind and 1 different? Either the different card is last, or it's in the middle, or it's first. I think those are the only ways to do it. And I mentioned this before. The hardest thing about probability is figuring out how to count stuff. And that's hard. So it turns out there's 3 different ways this can happen. And let's write down what happens for each of these. So we're going to need to summarize that on another page. So my options were match, match, not. And that was 52 out of 52 times 3 out of 51 times, 48 out of 50 for the not? Okay. The other option was match, not, match. And that was 52 out of 52, 48 out of 51, and then 3 out of 50, I believe. Yeah, right there. And then the last version of this happening from my tree was not match the last 2 matched. I didn't match the first king I got. There was a 52 out of 52 chance, 52 out of 52. And then there were 48, let's see, no. What was that one? Yeah, that was 48. There were 48 out of 51 cards that didn't match the king, and there were only 3 out of 50 that matched this card right there. What do you notice about all 3 scenarios here? Anything? Do they have anything in common?
They have the same numbers.
They have
maybe not in
exactly the same
order.
numbers, different order, so they're all going to come out to the same thing, whatever that decimal is. Like if we rewrote this as a decimal or fraction, they're all the same number. I just have 3 of them. So the final answer for the probability of 2, only 2 out of 3 alike is 3 times, well, that's really just a 1, times 48 out of 51 times 3 out of 50. How would this get harder? Well, pick a more complicated collection of cards to have in your hand. Get 5 cards instead of 4. But it's a logical process somebody could follow for more. If you're really bored one day, try to get 3 alike out of 5. That's a bit bigger tree. It hurt my head last time I did it. I think I had to do it 3 times before I was sure I was right. So probability is hard. It's about counting. Counting sounds easy, but sometimes it's not. All right. Stop this recording. We're done with probability.